Hi, people. What are you? So this is a scene from the movie Arrival, which is one of my favorite movies of all time. And in this movie, an alien species visits the Earth and initiates a dialogue with humans by producing sounds and by writing, creating these mysterious patterns on a screen. Amy Adams here plays the role of a linguist who's tasked with understanding the purpose of their visit. She does this by interacting with the species to understand their communication, while also trying to teach them a little bit of our own. Communication is a key characteristic of intelligence. Being able to create an infinite number of messages by composing finite sets of sounds is a key trait that distinguishes humans from other species on the planet. Understanding the communication system of another species, its complexity, its information carrying capacity, helps us understand their intelligence, their cognition, environment, and culture. In fact, it might also tell us a little something about how our own language system came into being. But before we start to think about alien communication, there are millions of life forms on Earth with distinctive sounds and communication strategies. They have their own physical and mental constraints and have evolved in their own unique ecosystems and societies. However, we know very little about each of their communication. So, how do we decipher the communication of another species and possibly even communicate back? Together with my wonderful advisors and the team of Project SETI, I study this question. Today, I'm going to show you how, as a computer scientist, I could contribute to this exciting project. Project SETI is a non-for-profit organization with researchers from around the world with backgrounds in robotics, cryptography, AI, linguistics, and however, it's mainly based out of the country of Dominica in the Caribbean, right, which is also home to the sperm whales. At Project SETI, we want to first understand the communication of sperm whales. Sperm whales are animals with the largest brains to have ever existed on the planet. They've had it for 16 million years longer than us. And sperm whales use sound to both echolocate and they use to perceive their environment as well as to communicate. They live in complex matriarchal societies with multi-generational bonds, where the members of the family coordinate their dives, engage in extended periods of socialization, and even take turns babysitting each other's young ones. While coordinating in complete darkness, they exchange long sequences of sounds with one another. So we know that they're communicating. We just don't know how they're doing it or what is it that they're saying, and that is what we've set out to find. Sperm whales sound like this. The communication sounds of sperm whales are believed to be made of distinct sequences of clicks that are called coders. Past research has identified around 21 discrete coder types in the Caribbean, and a subset of these have been shown to contain information about the speaker as well as their clan identity. However, almost everything else about their communication system, including questions about its structure and information carrying capacity, remains unknown. So what makes this problem challenging? Sperm whales live in a completely different ecosystem and can produce and hear sounds very differently than us. And unlike the setting from Arrival, the whales did not already come forth with the intent of communicating with us. So to start, we want to largely be able to understand their communication system through a static data set containing recordings of their sounds as well as behaviors. The other added complexity to this problem is the data collection itself. We do not want to study these animals in captivity and want to understand them in their naturally arising environment, like in the ocean, right? And do all this while being minimally invasive. So as you can imagine, collecting data of this kind is difficult and scarce, and the data like this is precious. So given data like this, what might the communication of sperm whales look like? Is it like the crab and cuttlefish, where a few fixed gestures indicate current environmental factors? Or is it like the vervet monkeys, where a handful of sounds and their paired combinations are used to warn the rest of the tribe of predators and their locations? Or is it like the human language, capable of conveying a range of complex meanings and fairly abstract ideas? One of the key differentiators between human communication and all known animal communication systems is this property called duality of patterning. It's how a base set of individually meaningless elements or phonemes get sequenced together to form words, which can in turn be composed to generate an infinite space of complex meanings. For example, the sound "b" here does not mean anything by itself, right? But it's combined here with other such meaningless sounds to give rise to the word banana, which is meaning-carrying, which is then in turn combined with other similarly created words to convey complex meaning. So getting to the point of understanding the communication of sperm whales will require understanding what features of their voices do they control, what forms the smallest set of meaning-carrying units or the equivalent of words, how are the sounds sequenced together in the course of an exchange, and what is it that they're communicating about. We've done some work on each of these questions. However, today I will only talk about the first. So these are the visualizations of the coders that we saw previously. And going into this project, we did not know anything about the whales and had no idea about how to even think about this system. However, we knew that until now, sperm whales were believed to produce only a small fixed set of coder types. And the contrast between the apparent simplicity of the system and the range of complex coordination behaviors that it enabled presented a fundamental mystery to researchers in the field. So the first thing we did was develop a few different ways of even looking at this data. One visualization we came up with was this one. So instead of plotting clicks in time this way, let's plot them along two axes. On the x-axis, the position of the dot will represent the time the click was made at. And on the y-axis, how long after the first click in the coder the click was made. Let's also do this for the other coders. And if we do the same thing for all the whales in the exchange, each represented with a different color, it'll look like this. Let's also connect the coders made by the same whales with lines. So this will help us see how the coders evolve over time. We call this plotting style the exchange plot. Visualizing coders this way enables magnifying and visually tracking how these coders made by individuals change over time. A 30-minute exchange between multiple whales then starts to look like this. The exchange plot already highlights so much more variability in the sounds of the sperm whales that the visualization of the clicks as dashes just simply fail to show. Let's take a closer look at one of them. The exchange plot magnifies the structure of the coders across dialogues, but also within every single coder at the same time. So when we plot the calls of the whales like this, they start to look a little bit like music. They have different tempos and rhythms. And also just by looking at this plot, you can see that they can change one feature without changing the other. Further, there are lots of other musical features, like these ornaments and ritorandos that we call rubato. In fact, some of these axes of variation in the calls only become noticeable in the context of the rest of the calls and are therefore contextual. But how do we know if they're controlled or just random noise in the production and the sounds? And how do we know that they're in fact intentionally controlled? Let's take the rubato, for example. If we take the sounds of a single whale, the changes between consecutive calls are sometimes of the order of nearly 100 milliseconds. So deducing what features of a sound are controlled is a question of not only what the individual sounds sound like, but also how they affect the behavior and responses of another whale. We find that this extremely delicate modulation of the duration of the coders is both perceived as well as imitated by responding whales in the exchange. So if it really were noise and imperceptible to a listener, how could it possibly be imitated? A more in-depth analysis of the sounds in the dataset showed that the codas are not defined by a small fixed set of coda types, as previously believed, but instead formed a combinatorial coding system, where coda types can be explained by combinations of the following 4 features, each of which can be independently varied. So similar to the International Phonetic Alphabet for humans, we propose the sperm whale phonetic alphabet. Our analysis suggests that the calls of the sperm whales contains 18 different rhythm types, 5 different tempo types, an optional ornamentation, and 3 different variations of rubato. The resulting set of individual symbols for this combinatorial basis can represent 8 times more information than what was previously believed, showing that the sperm whale communication system is significantly more expressive than what was previously thought. The existence of a combinatorial coding system at either the level of sounds, sound sequences, or both is a prerequisite for duality of patterning. And combinatorial vocalization systems are exceedingly rare in nature. However, their use by sperm whales shows that it may not be uniquely human and can arise from dramatically different physiological, ecological, and social pressures. These results open up the possibility that the sperm whale communication system might provide a very first example of that phenomena in another species. Additionally, SETI is building technologies that will allow us to collect a large amount of multisensory data in Dominica with a suite of different sensors. This will allow for round-the-clock recording of their sounds, aspects of their behavior, as well as the environment. Following that, this will also allow us to use more powerful machine learning techniques to analyze the data and perhaps get us closer to understanding the meaning of the sounds of the whales, and maybe even communicate back with them. Finally, hopefully the algorithms and approaches we develop in the course of this project will empower us to better understand the other species that we share the planet with. Thank you.
All right.